Okay, so page 3. Okay, I just want to kind of give a quick connection between last semester and this semester. And last semester was all about derivatives, right? I was just going to put a few notes up here. What's another word for derivatives? Slope, right? Right, slope of a point on the curve, right? Because we know that the unique thing about derivatives on the curve is that we're able to find the slope even though we only know 1 point, right? We don't need 2 points to find the slope at a point because we can use derivatives. But still, slope comes from the idea of change in y over change in x, right? Change in y over change in x. Okay. So we know that we developed the derivative idea from slope, which is coming from slope formula that we learned in algebra. Now, what operation is used here between y sub 2 minus y sub 1 and x sub 2 minus x sub 1? Division, right? So division. Now, if we want to undo division, what do we use? Multiplication, right? So I want to talk about what you see antiderivatives when you undo division. So let's say I had x sub 2 minus x sub 1 multiplied by y sub 2 minus y sub 1. So that means this is some change in x multiplied by some change in y. What do we get if we get this length times this length? What does that remind you of? Area of a what?
Square.
Okay, rectangle. Right. But yeah, I mean, it's the same idea, right? That length times width, if they're the same, then yes, they'll be a square. But if they're not the same, they'll be a rectangle. So we see that is really the connection here between derivatives and antiderivatives, is that if we undo the operation for slope, we get multiplication, and that multiplication is going to lead us towards area. So that's why area and slope are kind of inverse operations of each other, and that's what antiderivatives can do for us. It can help us find the area of a region, and that's what we're moving towards. That's why we're talking about area so much. We will talk about area so much because it, in turn, is the inverse operation of slope. Okay.
Is there ever a time where you have to solve for a derivative and go back and get the antiderivative?
Well, we're going to need to know some of the tools from the derivative side to be able to do the antiderivative. That's why we introduced this first, because this is the more complex thing to do. And so once we learn this, we are going to have to need some derivative knowledge to do antiderivatives. Okay. So the idea of Riemann sums is that we're going to be using rectangles first to estimate the area of a region. So right now, we're still not talking about the calculus aspect of it. We're just talking more about the geometric aspect of it, and that will hold true until tomorrow. Okay, so right now, today, we're just doing approximation of a region using rectangles. Right. So consider the function x squared plus 1. That's this curve right here. It's a parabola that opens up with the y-intercept at 1. Now, if I want to find the area of this curve, I'm not going to be able to rely on geometric shapes because this is not there's no geometric formula that can handle this, right? However, we don't care right now about actual area. All we care right now is creating some sort of approximation based off of however many rectangles they want us to use. So suppose we want to estimate the area of the shaded region using a given number of rectangles. Okay. Now, one way to do it is using upper rectangles. So upper rectangles is where we're purposely drawing rectangles where it's going to over approximate. Okay, portions of your rectangles will always sit above the curve. You can obviously tell that the area of these 4 rectangles will be a larger area than the area of this curve, or area under this curve, this shaded region, right? Because you have all these portions that's sticking out above the curve. Okay. Now, when you draw these rectangles, it's important that you are attaching one of the corners to the curve. Okay, so one of the corners will have to sit on the curve, either the left or the right. Okay. All right, so notice one corner from each rectangle is on the graph. This ensures that the height of the rectangle is the same as the value of the function. We want to use the value of the function to help us give the height of each rectangle. Okay. So this is region 1, region 2, region 3, and region 4. Okay. Now, if we want to ensure an upper rectangle is going to be produced for each region, what you want to do is you want to look to see between the 2 bounds, which one will produce the higher y value. So here, let's say this is -2, -1, 0, 1, and 2. We see that when I attach the graph to -2, it produces the higher y value. That's why this is representing the height of the first rectangle. Okay. Between the height at -1 versus the height at 0, -1 has the higher y value. So that's why the second rectangle is going to attach itself to the left, to the graph at -1. And then for the third region, we see that 0 and 1 has a higher y value. So we're creating a rectangle with the height at 1 because we purposely want to choose the higher region for because we want to do an upper rectangle. Okay. And then the fourth region, we see that between 1 and 2, 2 has a higher y value. So we want to use 2 at the height of the fourth rectangle. Okay, so this will ensure an over approximation of the actual area. Next up, what if we want to do a lower or inscribed rectangle? This is where we purposely want every rectangle to be below the curve because we want to guarantee an under approximation of the area. You can tell that the area of this region is going to be less than the area of the actual area, and obviously will be less than the over approximation. Now, for a lower or inscribed rectangle, what you want to do is for each region, you want to purposely look to see which of the endpoints will produce a lower y value. Whichever produces the lower y value is going to be where you're going to attach the graph to represent the height. Okay. So in this case, between -2 and -1, we see that -1 has the lower height. So whatever has lower height, we want that to represent the height of that particular rectangle. So here in the second region, between -1 and 0, 0 has lower height. So we want 0 to represent the height of my second rectangle. The third rectangle, between 0 and 1, we see 1 is up here, 0 is down here. So the third rectangle is also using 0 to represent the height of that third rectangle. And then the fourth rectangle, between 1 and 2, 2's up here, 1's down here. We want to choose the lower one. So we're able to draw 4 rectangles. Every rectangle has one of the corners touching the curve. Yeah, if we want a lower or inscribed rectangle, you want to choose the lower height of each region. If it's an upper rectangle or circumscribed rectangle, you want to choose the higher height from either corner. Now, these are not as common in terms of ones that we see on the AP exam and ones that we're going to explore. The ones that we're going to see more often are these left-handed or right-handed rectangles. This is where we don't care whether it's an over approximation or under approximation. We just want to choose consistently the left endpoint to represent the height of each rectangle. Or right-handed rectangles will be, we want to purposely choose the right endpoint of each rectangle to represent the height or the height of each rectangle. So again, region 1, 2, 3, and 4. Okay. We're just purposely choosing whatever the left endpoint of each subinterval, connecting that to the curve, and then making that forcing that to be the height of that first rectangle. Second rectangle, you want to choose the upper left corner. Third rectangle, choose the upper left rectangle, and then fourth region, choose the upper left corner. Okay, right-handed rectangles for each region, you're going to choose the right endpoint to attach to the curve and letting that represent the height of each rectangle. And notice the corner that I choose is based off of the it connecting to the curve. It has to sit on the curve. Okay, let's see if we can create one from scratch. Okay, so example 1, it says use 4 rectangles to estimate the upper and lower sum, so over approximation, under approximation, for the area bounded by x equals 0, y equals 0, x equals 2, and y equals x squared plus 1. So x equals 0 is the y-axis, y equals 0 is the x-axis, x equals 2 is this vertical line here, and then the curve is x squared plus 1. So we want to force 4 rectangles to represent the area of this region. And we know that it's just an approximation. We know that because of the curve, we're not going to get the actual area. We just care about finding the approximation based off what they're asking for. Now, the first step is you want to determine the width of each rectangle. We want every rectangle to share the same width. So to do that, we're going to have to go through this formula. Identify the left endpoint, identify the right endpoint, and also identify the number of rectangles that you want to use or that they want you to use. And then we go through this formula, b minus a divided by n. If we do this, then we can take our full interval, separate them into equal parts, and then we can find the width that we want each rectangle to have. Okay, we're going to draw the graph, which I've drawn for you already, and then we're going to find the sum of the area of the appropriate rectangles. And then we're going to do width times height for every rectangle to represent the area. Okay, so we're going from 0 to 2. So I have this graph sectioned off for us down here. Okay, let's find the width of each subinterval. So the width is going to be b minus a over n. Okay, what's my a and b value? Yeah, 2 and 0. And n is the number of rectangles. How many rectangles do we want? 4, right? So the problem will always tell you how many rectangles you're dealing with. So in this case, we have 2 minus 0 over 4, okay, and that reduces to be what? 1/2. Okay, so then you're going to take that 1/2 and you're going to increment that value, and then we're going to keep going until we reach 2. So if I add 1/2 to 0, I get 1/2. That's my first subinterval, my first boundary. Next up is what? 1. Next up is
3/2.
Yep, 1.5 or 3/2, and next up is 2. So if I add my width correctly, then I should be able to end up at my right endpoint. Okay, so if you somehow get the wrong width, or if you add incorrectly, if you get the wrong, if you're not able to reach this point, then something went wrong. Okay, so you should be able to start at the left endpoint, add the width, and eventually reach exactly your right endpoint. Okay, so yes. Question. How to get to 0? So it says the area is bounded by x equals 0 and x equals 2. Yeah, so yeah, the boundary will always be provided for you in the problem. You never have to guess what the boundaries are or the number of rectangles are. So let me label this here. So this is my first region, second region, third region, and fourth region. Okay, we're going to start off by doing the upper sum. Okay. So we're going to force every rectangle to sit above the curve. So between 0 and 1/2, which has the higher height on the curve? 1/2, right? So you're going to highlight 1/2, and then you're going to draw a horizontal line over because we want to force 1/2 to represent the height of my first rectangle, right? We want an upper sum here. Second region, which has the higher heights on the curve. At 1, right? So highlight 1, and then you're going to force that to be the height of the second rectangle. Okay, third one. Which one is higher height? 1 or 3/2? 3/2, right? So this is consistent, right? Because the graph is always increasing. So if the graph is increasing, then the right endpoint is always going to represent the higher height. And then the fourth rectangle, 2. I'm going to lightly shade in just so that we can clearly see that we're just trying to find the areas. We're going to just find the areas of each rectangle and add them up. That's all we're doing. Okay, I'm going to use uppercase S to indicate that I want to use upper sum, and then 4 to indicate that I'm using 4 rectangles. Now, what's the width of every rectangle? 1/2, yeah. So my first rectangle is width of 1/2. And the height of my first rectangle, I'm going to find the height later. Right now, I want to leave it in function notation. I'm going to say f of 1/2, because this is my f of x function. So whatever f of x is, if I plug 1/2 into the function, that will give me my height. So f of 1/2 is not the actual value. It's just telling us how to get to the height. All right, so that makes sense. This is right now. We'll get it out of function notation in a second. But right now, I just want us to represent our width and height. Width is exact, but height is represented in function notation. Okay, second rectangle. Width is still 1/2, and the height I can represent as f of what? 1. Yep. Okay, third rectangle, width times height, 1/2 f of 3/2. Last rectangle, 1/2 f of 2. Now my function is x squared plus 1. So if I plug 1/2 into the function, I'll get 1/2 squared plus 1. That'll give me a fractional value. I multiply that by 1/2, and that will give me the area of the first rectangle. Okay. Plug 1 into the function, I get 1 plus 1. 1 plus 1 times 1/2 will give me the area of the second rectangle, so on and so forth, right? Does that make sense? Getting the actual area, okay? So this is what results from our upper sum. The first rectangle is 0.625. And you'll get to use your calculator, so it's really just the setup that I'm really after here. Because if I were to plug 0.5 into the function, I'll get 1/2 squared plus 1, which is 1.25. Multiply that by 1/2, I'll get 0.625. So the area of my first rectangle is 0.625. Area of my second rectangle, area of my third rectangle, area of my fourth rectangle. I add this up, I get that number, and that number represents an over approximation of the actual area.
What did you make the that? But then
Sorry.
you said over approximation. So what do you do to make like exactly?
Right. So to get to the exact area, we're gonna have to need calculus. So we'll do that later. But right now, we're just focusing on getting the approximation, because eventually the calculus will help us get to where we need to be.
What does the S think?
The S just represents this is the upper sum.
Okay.
And then the lower S will represent the lower sum. So hopefully I know it's a lot of numbers here, but really we're just adding rectangles, right? Width times height, width times height. You're finding the width, you're finding the height, and you're just getting there. Now, even though this is not calculus, this is part of this idea of Riemann sums. Approximating an area is part of the AP exam. Okay, so we do need to be able to approximate area using rectangles. So it is a calculus topic, even though it's just geometry. Okay, so part B, finding the lower sum. Again, we're going from 0 to 2. Our intervals are all the same, right? 1/2, 1, and 3/2. But now we're purposely choosing the lower height of each subinterval to represent the height of each rectangle. So here, between 0 and 1/2, we're going to choose 0. Between 1/2 and 1, we'll choose 1/2. Between 1 and 3/2, we'll choose 1. Between 3/2 and 2, we'll choose 3/2. So lower sum for. Again, let's write this out in function notation, and then we'll just convert them to decimal values. Again, the width of every rectangle is what? 1/2. Now, this is something that we could do, is that we could have factored a 1/2 out previously, right? And then just added up. Added up the heights. So sometimes you might see that in the multiple choice question where they're factoring out the width because they're all the same. So these mean the same thing. So you can do that if you want. Right now, I'll just leave everything as separate, so it feels more consistent. What will represent the height of my first rectangle? Good. So now I got to start on the left side, because the left side, the graph is always increasing. So the left endpoint of each subinterval will be the lower one, right? Yep. So we're just going to go down the line. We're basically going to reuse every one of these. It's just that we're not going to use 2, right? F of 2 is not going to represent any left side of any rectangle. Yep. Now, if we get the area and add them all up, it should be a lower number than what? Yeah, it should be lower number than upper sum, right? If we're doing this correctly, then the lower sum should be, my under approximation should be smaller than my over approximation. Okay, so I'm just doing all the math here for us here. Just plugging it into the calculator. I get 3.75, and then 5.75 being the over approximation. Now, some students have asked, well, can I just find the average of these two and that will be the exact area? Now, if I find the average of these two, I will get a better approximation, but it's not anything that we're ever going to have to. Well, first of all, it's still an approximation. It's not going to be, the area is not going to be exactly between the upper and lower sum. And second, this is not a number that we're going to use from what we're going to, they're never going to ask for the average of the upper and lower sum. All we can say is that this is a better approximation than these two, but this is not something that we're really going to use. But it is, in essence, it is a better approximation than these two, but yeah, just, we're not going to have to worry about, oh, find the average of the upper and lower sum. Okay, there's one more type I want to show you, and that is a middle approximation. Middle rectangles is where instead of choosing the left or the right endpoint, we're choosing the midpoint to attach to the curve, which will give us a better approximation because we have portions of the rectangle that will stick above the curve and portions that will stick below the curve. And so it'll kind of average things out. Okay, let's go to the next stage. Okay, so the midpoint rule is similar to the upper and lower sum in the sense that we're still using rectangles, but we're going to use the midpoint of each rectangle to calculate or represent the rectangle's height. So we're still, let's say we had a curve 8 over x squared plus 1. That's represented by this curve here. We're going from 2 to 6, and we want to use 4 subintervals. So I'm doing some of the work for us here already. The width is still b minus a over n, but my a and b values are 2 and 6, and my n is 4. So 6 minus 2 is 4. 4 divided by 4 is 1. So every subinterval is going to be 1. So if I'm starting at 2, I'm going to 6. My next subinterval will be 3, 4, and 5. Okay. Now, what is the width of every rectangle here? 1, okay? We know that's going to be the width of every rectangle. Now the height, we're not going to use f of 2 or f of 3. We're going to use whatever is between 2 and 3. So what's the midpoint between 2 and 3? 2.5. So we're going to insert 2.5 into the function, and that will represent. So I'm going to use the midpoint or the middle rectangle approximation here. The width of my first rectangle is 1, and the height of my first rectangle is f of 2.5, right? I'm just attaching wherever 2.5 is to the curve. And this is, I drew the rectangle here to show what that rectangle could look like. And you can tell that this is going to be already a better approximation than the upper or lower sum, because the fact that you have rectangles that stick above and below the curve, it'll help to kind of balance things out, right? Plus, what's this? What's the area of my second rectangle? 1 times what? Yep. And define f of 3.5, we're just going to insert 3.5 into the function. Whatever that decimal value gives us, that's the height, right? But right now, I'm just having us practice writing it out in function notation. Okay, question? Yes.
I don't get how you got like 4.5.
Got it. So you see how f of 2 and f of 3, this f of 2 and f of 3 will represent the left and right endpoint of the first subinterval. But we want to use the midpoint. So what's between 2 and 3? 2.5. So that's why we want to use 2.5 as, I'm sorry? Exactly. Yeah, this is the third way. We have the left-handed rectangle, right-handed rectangle, and then we have the midpoint rectangle. Now, technically, there's also upper and lower sum, but we're really not going to see that much more after this. We're really just going to see left, right, or middle. Yeah.
Do you recommend using the decimal values instead of fraction?
It's up to you. Yeah. Okay, and then we're literally just inserting 2.5 into the function, and then getting that decimal value, and then adding them up, and then getting my midpoint sum. Okay, I like for us to try some of the homework problems that are going to be assigned to you tonight. So if you can turn to page 47, which is the same page that you were doing homework from last night. Now, 47, I wanted us to work on page 31, 32. but I realized that these are kind of small for us to see, and it's not very clear. So what I did was I took these problems and I copied it again, and I put them on page 48. That way we can work directly on this sheet of paper, and it just feels a little cleaner having everything in front of you like this. Okay, so it says find the upper and lower sums. 31 and 32 bound the area of the shaded region by approximating the upper and lower sums. Use rectangles of width 1. So we already they're already telling us some information about this. Okay, it says find the upper sum from 1 to 4. So notice that 1 to 4 has already been highlighted. I'm going to say this is region 1, region 2, and region 3. Now we want to find the upper sum. So we want to force every rectangle to be above the curve. Okay, so then for region 1, which has the higher height? F of 1 or F of 2? F of 2. So you're going to highlight F of 2 and drag that over to represent the height of your first rectangle. Between F of 2 and F of 3, or the second region, which has the higher y value? F of 3. Okay. Between F of 3 and F of 4, which one has a higher one? F of what? 4. So it ends up being the same as a right-handed rectangle, right? Every rectangle, we're using the right endpoint to attach to the curve. Okay, so then let's find the area, or at least to the best of our ability, of these 3 rectangles. What's the width of my first rectangle? 1. What's the height of my first rectangle? F of 2, which we can just go ahead and say it's equal to what? What's the height of my second rectangle? 4, yeah. Okay, width of my second rectangle? 1. What's the height of my second rectangle? Yeah, our best approximation looks like it's 4.5, so we'll just stick with that. And then third rectangle, width of 1, height of 5, yeah. 13.5, right? Okay, let's find the lower sum. Same region, same number of subintervals. But this time we're going to choose, yeah, the left one because it's always increasing. So my left endpoint will always be sitting lower. Right? It makes sense that my lower sum is smaller than my upper sum. Okay, let's see if we can finish up 32, upper sum and lower sum. Okay, upper sum between 1 and 5. So I have region 1, 2, 3, and 4. So I have 4 regions here. Width is 1. Upper sum. So for each subinterval, you want to choose the higher of the 2 heights. So between 1 and 2, which one has the higher height? 2. So you want that to represent the height of your first rectangle. Between 2 and 3, which one has a higher height? 2. So looks like we're going to use f of 2 to represent the height of both the first and the second rectangle. So because the graph here is not always rising or falling, we could have some shared heights between rectangles. Between 3 and 4, which one is higher? 3. So highlight the graph at 3 and force that to be the height of that rectangle. Fourth one. Okay. Width times height, that's pretty straightforward. I want to help draw the lower sum here, in case we run out of time. So, okay, between 1 and 2, which one has the lower height? 1. Highlight where the graph touches or where the curve is. Okay, between 2 and 3, for the second subinterval, which one has the lower one? 3. So make that the height of the second rectangle. Between 3 and 4, 4. Okay, now this one is a little bit strange here. Between 4 and 5, which one is lower? 5. So that means for the fourth rectangle, it's just going to be 0 because the height is 0. So you're basically having to just rely on 3 rectangles to get the lower sum because I can't pick this one. This will be up higher, so I'm just having to choose that to be 0.
51 times.
Yeah, 1 times 0 for that fourth one. Yeah. Okay. So you can do some of the homework problems directly on this. I also put 33 and 36 on here. Okay. So check your calendar. But the rest, make sure you put it on a separate sheet. All right, come get your phones. It's just this. Yeah, I just have my website and I record my videos. You post on your website. Yeah, post on my website. Yeah. Okay, cool. You know, yeah, I think I sent a link to that.
Yes, I was on the website last
Okay. Huh?
There's no like one.
Yeah, no one, no. The only time I'm going to use Teams is if I have a help session in the morning and I send a Teams link to you if you want to join virtually. If you're not joining virtually, you can come here in class as well. That's the only time I'll use Teams. You're right. Yeah. Yeah. Some problems, you're right. It just shows you the solution, doesn't show you.
Yeah, and that's why I didn't know.
That's why you didn't know. I got it. Okay. But at least, you know, you can at least write it down to show me that you looked at it. Okay.